Imagine a world where females hold all the genetic cards, and males are, well, let's just say they're playing with a different deck entirely. This isn't science fiction. It's haplodiploidy, and it's happening right now in beehives and ant colonies across the globe. So what exactly is haplodiploidy? At its core, it's a genetic system where females are diploid, meaning they have two sets of chromosomes, one from mom and one from dad. Males, on the other hand, are haploid, having just one set of chromosomes, inherited solely from their mother. This haploid-diploid divide is the key to understanding this fascinating system. Let's break it down using our favorite honeymakers as an example. In a beehive, the queen bee can lay two types of eggs, fertilized and unfertilized. Fertilized eggs develop into female worker bees or future queens, while unfertilized eggs become male drones through a process called parthenogenesis. And here's one peculiarity that might blow your mind. A male bee has no father and cannot have sons, but he does have a grandfather and can have grandsons. But how exactly do females control this process? Well, it's all thanks to a fascinating internal organ called a spermatheca. After mating, each fertile female stores sperm in this specialized sac. As eggs pass down her oviduct, she can choose whether or not to release sperm from her spermatheca. If she does, the egg is fertilized and becomes female. If not, it remains unfertilized and develops into a male. This level of control over offspring sex has some remarkable implications. In social species like bees, wasps, and ants, it allows colonies to adjust their sex ratios to maximize relatedness among members and create a workforce that's perfectly suited to their environment. But the story doesn't end with social insects. In solitary hymenopterans, females often lay unfertilized male eggs on poorer food sources, while placing fertilized female eggs on premium real estate. Why? Because female offspring are more sensitive to early life shortages, so mom gives them the best start possible. And let's not forget about the haplodiploid ambrosia beetles. These tiny ecosystem engineers adjust their offspring sex ratio based on dispersal opportunities. When males have a better chance of finding mates in new locations, mothers produce more sons. Haplodiploidy is found in all members of the Hymenoptera order. That's ants, wasps, and sawflies too, and even in some mites and thrips. Now you might be wondering, how did this fascinating system come to be? Well, the evolutionary history of haplodiploidy is a bit of a mystery. But here's a clue. Haplodiploidy seems to have evolved most commonly in insect species that nest in bark, home to a bacteria called Wolbachia. Wolbachia is a sneaky little microbe that infects the ovaries of insects. Scientists think there might be a connection between Wolbachia infections and the development of haplodiploidy. It's like these bark-dwelling insects and their bacterial tenants co-wrote a new chapter in the book of evolution. Haplodiploidy isn't just a biological curiosity. It's a powerful evolutionary tool. It allows for rapid adaptation to environmental changes and helps remove harmful genetic traits from a population more efficiently than conventional genetic systems.